There are 10 sections to this lesson, and rather than watch the whole thing, you may want to jump to the particular graph shape you're interested in. To be able to draw a curved graph smoothly and accurately, you have to have a sufficient number of points. Almost always far more than you'd have to have for a straight line graph. Here I have a table of results for y equals x squared for values of x from -10 to +10. To draw a useful and accurate graph, you need to use as much of the graph paper as you can, which means you have to think ahead and calculate a scale that will do just that. In this case I can see that for x I've got -10 to 10, that's 20 divisions. And fortunately there are just over 20 centimetre squares on the graph paper, so I'm using 1 division, 1 centimetre for each unit of x. And on the y-axis, which has to reach 100, I'm using 1 centimetre for 10 units. It is of course important to plot each point as accurately as you can. But here, since the points were calculated, I would expect the curve to be smooth. Those obtained from experimental results are likely to be rather more irregular, and you have to take account of that as you draw. In order to draw the curve as smoothly as possible, put your hand on the inside of the curve, and as it sweeps around, the natural curve of the line should, at least closely, with a bit of control, follow the required curve of the graph. You can see I'm no artist, but at least it is reasonably neat and tidy. However, drawing graphs by hand is rather tedious and slow, and this lesson is about graph shapes. So I'm using Excel spreadsheet to generate the figures and to draw the graphs for me. This graph, y equals x squared, results in a parabolic curve. Y is always positive because squaring a negative number still results in a positive result. If we change the parameters so that y equals 3x squared, we get a sharper curve. And if we add or subtract a number to the equation, then it either lifts or, although I haven't shown it, lowers the curve. The equation y equals x cubed will not result in all positive values of y, because when a negative number is cubed, it still ends up negative. And because it's cubed, some of the values of y are very high. The curve shape ends up like this. Plotting a graph y equals the square root of x, we cannot use negative values of x, because the square root of a negative value is not a real number. The curve here is not very smooth, partly because we have no values of x below 1, and partly because the calculation of the square root is only to two significant figures. By correcting both of those, the curve is very much more smooth and more accurate. In plotting an inverse graph, y equals 1 over x, any value of x which is greater than 1 will result in a value of y which is less than 1. And a value of x which is 0 produces infinity, a false result. To produce a full smooth graph, we need values of x inserted which are between 1 and -1, but not 0. The graph produced shows two curves, one for negative and one for positive values. Where x is a power, so that y equals a number to the power x, we produce an exponential graph. The term exponential is common in everyday language and refers to something that is increasing very rapidly. And as you can see here, the values of y on this graph also increase very rapidly. Although at very low values of x, those below 1, and negative values of x, the value of y created is very small indeed. The constant used here, e, has an approximate value of 2.72. It is the natural logarithm base and occurs in many equations. In these first log graphs, I'm using logs to the base 10. When we look up the value of a log, what we're trying to find is the number, which if it's used as a power of 10, will equal x. So, for example, if we have 100, the log of 100 is 2, and that's because 10 squared is equal to 100. And the log of 1000 is 3 because 10 cubed equals 1000. The logs of numbers between 100 and 1000 are between 2 and 3. The logs of numbers between 10 and 100 are between 1 and 2, and the log of a number below 10 is a decimal fraction. It is between 0 and 1. There is no such thing as a log of a negative number because you cannot raise 10 to a power and get a negative result. The graph shape then is produced from the logs of numbers between 1 and 10, and this is the typical log graph curve. If a graph is plotted of the natural log of x, that's logs to the base e, then the shape of the curve looks exactly the same, although the values on it are different. Before we look at trig graphs, that's graphs of sine, tangent and cosine, I'll explain that the angles that are used for the values of x are measured in radians. A radian is the angle at the point of this arc. The distance around the edge of the circle is r, equal to the radius of the circle. It is very important to notice that this is not an equilateral triangle because the one edge is curved. If it were an equilateral triangle, each angle would be 60 degrees, but a radian is slightly less than that. You'll know that the circumference of a circle is 2 pi r, so there are 2 pi radii that fit around a circle. And so from our definition of a radian, there are 2 pi radians around a circle, which are equal to 360 degrees. If we divide the 360 by 2 pi, we therefore get the value of a radian in degrees, which is approximately 57.3. Moving back to the graph shapes of cosine, sine and tan x. Starting with cosine x, if I use the values of x that I've used up to now, of -10 to 10 in steps of 1 radian, then the graph we get is somewhat irregular, and that's because there really are not enough points on this graph to plot the curve accurately. To avoid the irregularity of this curve, I'm going to use values of x which are in steps of 0.25 radians and over a slightly smaller range. The graph produced is rather more even and regular, and I'm sure you'll recognize it as that for a sine or cosine graph. Now, the shape is the same for a sine graph, but not exactly the same values. If we lay on top of this the sine graph, the graph of y equals sine x, using the same range of figures, you can see that the curve, yellow in this case, follows exactly the same pattern, but is shifted along the graph axes. So where the cosine of 0 is 1, the sine of 0 is 0. The cosine of pi over 2, that's 90 degrees, is 0, whereas the sine of pi over 2, 90 degrees, is 1. For the graph of y equals tangent of x, I've used even smaller divisions of 0.05. Again, without these small divisions, this curve would not be smooth. But even so, it is irregular, because you can see that the peaks of the spikes of each part of the graph are at different heights, and they should not be. And that's because the tangent of pi over 2, or 90 degrees, is infinite, and I have not actually used a number which is exactly that value. Thank you for watching.